first session of welcome to the first session of Mind NZ Combinatorics. Um, so we'll go over what is combinatorics, an overview of content, and an introduction to me. So it's an area in math that's concerned with counting, and it ranges from all levels of math competition, from pretty simple math competitions such as AMC 8 to pretty advanced Olympiads, such as the NZMO and the IMO. And it involves lots of critical thinking, and you must have lots of versatile tools and be very flexible in order to solve these types of questions. And this is probably the content that we'll cover over the course of, I think, 6 combinatorics lessons. We'll do the basics, binomials, stars and bars, counting, Pascal's triangle. We'll do counting of conditions. We'll do the pigeonhole principle, invariance, examining extrema, and basic constructions. And this is an introduction to me. I'm a year 13 student at Rangitoto College. My hobbies are sleeping and eating. My favorite book is the Iliad, and my favorite number is 1. Does anyone have any questions at this stage of the lesson? Okay, then let's move on to the lesson. So today we'll have an introduction to counting, going over basic principles such as the addition principle, the multiplication principle, counting with order and without order. And then after that, we'll go through stars and bars, and then binomials and the Pascal's triangle. So what is counting in Math Olympiad or math competitions in general? Counting is a section of combinatorics where you have to deal with the question of how many, so such as how many ways can you arrange this, how many ways can you choose this, and it involves lots of creative and critical thinking. So we'll go through the first basic principle of counting, the addition principle. So if you have two different tasks, A and B, 1 and 2, and there are A ways to do the first task and B ways to do the second task, and both tasks are different and don't overlap, such as a section of B is the same as a section of A, then that would be overlapping. So none of them are overlapping. Then the total number of ways to do either task is A plus B. It's pretty intuitive, right? So if you have 8 oranges that are distinct, which means they're all unique, and 3 apples, which are all distinct as well, then how many choices of fruit do I have? Can someone tell me in the chat? Yeah, that's right, Chris. We have 8 plus 3, which is 11. And the most important condition for this is that they're mutually exclusive, which means they do not overlap. So when they overlap, what do you think happens? Can someone tell me in the chat? Does anyone have any idea what happens when the two tasks we're dealing with overlaps? Not quite. They don't multiply together. That's a different scenario. When they overlap and we still use the original method of counting, the addition principle, then we will overcount this overlap. Yeah, so using addition principle will overcount the overlap. And in the example, if we have 25 students in the math club, 25 students in the biology club, and 10 students in both, then if we use direct addition of A plus B, then we have 20 plus 25 equals 45 students. But that's clearly wrong, right? Because the number of students has 10 students in both, which means there's 10 overlap. So we have to subtract 10 from this sum of 20 and 25. So we have to do 25 plus 20 minus 10, which means it's 35 students instead of 45. And this is more formally known as the principle of inclusion-exclusion, which is pretty advanced. The next basic principle of counting is multiplication principle. If a task has multiple stages, such as one stage involving A ways and the second stage involving B ways, then the total number of ways to do both of these stages, or the whole task comprised of two stages, is A times B. So if you have a menu with like 3 entrees, 3 main courses, and 4 desserts, how many ways can you order your meal? Can someone tell me in the chat? Yeah, that's correct. You have 3 times 3 times 4, which is 36 ways. Yeah. So I'll give you guys 30 seconds to try these quick refreshers. How many? Oh, wait, no. I'll give you guys 30 seconds to try the first question. How many integers from 1 to 100 are divisible by 3 or 5? Okay, so I see a few answers in the chat. The answer is indeed 47. So can someone tell me in the chat why direct addition will not work in this case? Yeah, because they're not mutually exclusive, right? Because we have numbers that are divisible by both 3 and 5, which are the numbers that are multiples of 15. Lol, can you please mute yourself? Thank you. Okay, we'll do the next refresher. If you roll a dice and flip 3 coins, how many total outcomes are there? I'll give you guys 30 seconds to try this question. Yeah, the answer is 48, right? Because we have 6 possible outcomes to roll a dice, which is the first stage of this task. And then the next stage is flipping a coin, which has 2 possible outcomes. And then after that, we flip it again, which has another 2 possible outcomes. And then we flip it again, which has another 2 possible outcomes. And if we multiply all of these together, because they're stages of one task, then we get 6 times 2 times 2 times 2, which is 48. So now we'll move on to a bit of harder counting, I guess. So this is permutations. A permutation is defined as an ordered arrangement of items. Usually in math competitions, when you refer to a problem that uses permutations, you try to find the number of ways to arrange this. So you'll probably see questions that ask, in how many ways can I arrange all of these items? So this is an example. In how many ways can you arrange the letters A, B, and C? You have ABC, ACB, BAC, BCA, CAB, and CBA. So you have 6 ways, or 3 times 2 times 1, which is 3 factorial. So the basic derivation of this is the number of ways to arrange n distinct items in just, I guess, n positions. is we assign a unique position to each item. In the first position, we have n choices, right? Because we haven't used any of the items yet. In the second position, since we've already assigned a position to the first item, then we only have n minus 1 choices left, right? And then in the next one, we have n minus 2 choices until we have in the nth position, we have 1 choice. So we can view all of these positions as stages. And when we count the number of total outcomes for a task involving stages, which principle do we use? Can someone tell me in the chat? We use multiplication. So we multiply n by n minus 1 by n minus 2 all the way to 1. And that is called n factorial. So this is the more general formula of a permutation. If you permute n items, if you choose r items in some order from a set of n distinct items, then it should be n factorial over n minus r factorial. Does anyone know why? Why is it so, what does it look so complex? And what does this mean? So it's the same principle as what we just did before, but instead of doing all n items, we only look at r of them. So in the first position, we have n choices. In the second position, we have n minus 1 choices. In the third position, we have n minus 2, until the rth position, where we have n minus r plus 1. And then when we multiply all of these together, we get n times n minus 1 times n minus 2 times all the way to n minus r plus 1. And does anyone want to show us why n factorial divided by n minus r factorial is equal to what I just said? You can type it into chat. So essentially, when we have when we have n times n minus 1 times all the way to n minus r plus 1, then we have this number, and then we can multiply this by n minus r factorial and divide it by n minus r factorial to get the same number, right? Because we're just multiplying, dividing by the same number. And then on the top section, this turns out to become n factorial. And on the bottom section, we have n minus r factorial. Oh. Which gives us this general form of NPR equals this. Or in the formula in the slides, I think it says, yeah, P n of R is equal to this. Now we'll do combinations. So in permutations, we cared about order, right? Because a permutation is an ordered arrangement of items. But for combinations, order does not matter. So we just choose R items from n possible distinct items. And then to derive the formula for the number of combinations, we can start off with the number of permutations. So remember that the formula for number of permutations is P n r equals n factorial divided by n minus r factorial. Can anyone tell me the formula for combinations? Kingsley asked a question about y. Can you please elaborate on your question? Do you want me to explain this formula in more detail, or do you want me to explain something else? Oh, y is m minus r factorial on the bottom. So I'm pretty sure that it's just there for convenience, because we have that the number of permutations is n multiplied by m minus 1 all the way to n minus r plus 1, right? But then this is a bit tedious to write every time we use p of n and r. So we can just use something that takes up less space and is easier to write, which is n factorial over n minus r factorial. It's also easier to use on the calculator, but they're the same number. Does that make sense now? Okay, so this is the derivation for combinations, the number of combinations. So for each arrangement of a permutation, oh no, for each combination, it should correspond to all possible arrangements of those chosen items. So if we choose R items from n distinct items, we can just view it as a group of all possible permutations of those R items. That might sound a bit complex, but then, so if we have the permutation formula, then we know if we choose R items in some order from n distinct items, we have n factorial over n minus r factorial, right? Equals p of n and r. Then for c of n and r, I wrote c of r and n. For c of n and r, then it's basically just p of n and r, but we don't care about order, right? So we can just find a correspondence between a group of permutations that use the same elements or same items, and then we can just correspond that to one combination. Does that make sense? Yeah, which is why we divide by all the possible orderings of R items, because we choose R items, right? Which is R factorial. In the first position, we have R possible items, and so on until the rth position, we have one possible item. Which is why we do C of n and r equals P of n and r divided by R factorial, which is how we get this equation. Oh yeah, C of n and r can also be viewed as this. Can also be like tall brackets n r with n on top of r. So this means n choose r. We choose r items from n. So here are some practice problems. A game uses a deck of n different cards where n is an integer and n is larger than or equal to 6. The number of possible sets of 6 cards that can be drawn from the deck is 6 times the number of possible sets of 3 cards that can be drawn. Find n. This question is pretty hard, so don't be sad if you can't solve it. I'll give you guys 1 minute to try this question. Kingsley, why are you confused?
Just a bit confused about the question.
So it's basically saying that the number of ways you can choose 6 cards from n cards is 6 times the number of ways you can choose 3 cards from n cards. Does that make more sense? Okay, that should have been enough time to get a brief start on this question. Does anyone have any ideas on how we can start solving this question? What does this question ask? Or what does the problem statement say? Can someone tell me in the chat? Okay, this question basically says that n choose 6. Yeah, it's asking to find n. It's basically saying that n choose 6 equals 6 times n choose 3, right? Right. Yeah, because uh, each possible set of 6 cards is just the number of possible sets of 6 cards is just n choose 6, and the number of possible sets of 3 cards is just n choose 3. Right, because they say I think all cards are different. It says n different cards. So what does this mean? So we can expand both sides. N choose 6 is the same thing as n factorial over a 6 factorial times n minus 6 factorial. And n choose 3 is n factorial over 3 factorial times n minus 3 factorial. Right? And then lots of terms can cancel, and we get that n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 over 6 times 5 times 4 times 3 times 2 times 1 is equal to 6 times n minus 1 times n minus 2 divided by 3 times 2 times 1. Right. And then from this, we can see that a bunch of these terms also can cancel. We have that the 3, 2, and 1 on both denominators cancel, and we have that n minus 1, n minus 2 both cancel on both sides. So we have, after we cancel this, we can move the new denominator to the other side to make this more simple. And we get n minus 3 times n minus 4 times n minus 5 is equal to 6 times 6 times 5 times 4, right? Which means n minus 3 times n minus 4 times n minus 5 equals 720. Is everyone following? Yeah. Okay. And we know that if n minus 3 times n minus 4 times n minus 5 equals 720, then these numbers, which are pretty close, right? Because they're just adjacent numbers. They're consecutive numbers, right? They're in the form of a plus 1, a plus 2, or we can do a minus 1, and a plus 1, right? These are pretty close numbers, and they multiply to 720. So this is a strategy to find them, but it's not very accurate. It was on the Art of Problem Solving website though. So if you have three numbers that are really close to each other and they multiply to some number, we can just approximate by finding a cube number that's really close, right? What's a perfect cube that's close to 720? Can someone tell me in the chat?
Nine cubed is 729.
Yeah, 9 cubed is 729. Which is oddly very close to 720, right? It's 9 times 81. And then if you look at it, we have 729 minus 9 equals 720. So we have 9 times, oh, whoops. We have 9 times 80 equals 720, right? And then what are some factors of 80? We have 80 and 1, 40 and 2, 20 and 4, 16 and 5. But then we also have 8 and 10, right? Yeah. So we have 8 and 10. And now we know that 8 times 9 times 10 equals 720. So we know that n minus 3, n minus 4, and n minus 5 must equal 10, 9, and 8. n minus 3 equals 10. What does this mean? This means that n equals 10 plus 3 equals 13. And we are done. Does everyone understand why we did that and how we got the answer? Okay, I'll just take the silence as a yes. So now, let's have some quick questions. What is n choose 1? Can someone tell me in the chat using this formula? N factorial over r factorial times n minus r factorial.
Is n 13?
Oh, that was the answer to the previous question.
Oh,
In this one, n is just n. N is just any number, just n. What is n choose 1? Can someone tell me in the chat? It's not that hard. Okay, using the formula might take you some time, but then you can also view it as choosing one item from n distinct items. How many ways can you do that? N, right? Because you can just choose each item one time and that's it. And then what's n choose 0? You choose nothing from n items. Are you sure it's 0? Okay, the answer is actually 1 because 0 factorial is, well, no, because 0 factorial is 1 and also because you can always choose nothing from n items. That counts as one thing. And what does n choose n? Yeah, if you choose n items from n distinct items, there's only one way to do that, right? You just choose all of them. And next, prove that n choose r equals n choose n minus r. I'll give you guys 30 seconds to think about this. So basically, we can just use the formula, which says that n choose r equals n factorial over r factorial times n minus r factorial, and then if we put that on both sides, we have n factorial over r factorial times n minus r factorial. And then on this side, we have this is equal to n factorial over n minus r factorial times n minus r factorial. And then if we simplify this, we get this expression is equal to n factorial over n minus r factorial. And then over here we have the n's cancel out and we have double negative. So this is a positive times r factorial, which is the same thing as n factorial over r factorial times n minus r factorial. I think we can skip handout problem 1. It's pretty difficult, but there was a typo. You can do it in your spare time if you feel pretty confident, but it's very hard. I accidentally forgot to type 8. So the question originally said that let S be the increasing sequence of positive integers whose binary representation has exactly 8 ones. But then I forgot to put the 8, so it just says exactly ones. So now we'll cover stars and bars. This is also known as sticks and stones, ball and urn, or bots and dividers. So this is used when we need to count the number of ways to distribute identical objects, which is called stars in this case, into distinct groups or boxes using bars as dividers, which is why it's called stars and bars. And then this can possibly allow empty boxes. So in some groups we might have 0, and in some groups we might have all of them. And this can also be turned into the problem of x1 plus x2 plus all the way to xk equals n. where x1 all the way to xk can be non-negative, or are non-negative, which means they are 0, 1, 2, all the way to n. So we have a visual representation of this. If we split 6 into 3 groups, then how many ways can we do this? So essentially, the bars separate the groups of stars, right? I'll show you this on this whiteboard. So originally we have like 6 stars. And then the bars divide them into groups. So over here, we have 3 groups, right? But then to divide some number of things into 3 groups, we only need 2 bars, right? Because if we have like a line, then and we divide it with 2 things, then it already becomes 3 groups. So over here, we just need to find places to put our bars. So we can put a bar over here, and we can also put one over here. But then we can also put it over here, and also over here. And also we can put it, I think, over here and over here. You get the idea. Oh, and we can also put in the same gap, like this. But this basically divides all of the stars that we have into groups using bars. Oh, someone's asking how we can access the whiteboard. Oh, wait. How to share the whiteboard link, sorry. So this is an example of stars and bars with 6 stars and 2 bars. Note that the number of bars is equal to the number of groups minus 1. So over here, we can split it into 2 stars, and then we have a bar next to the 2 stars, and then we have 3 stars, and then a bar next to the 3 stars, and then 1 star. Can anyone tell me how many stars are in each group? I think I said it below the thing. Just type it into chat. How many stars are in each group? We have 2 stars, 3 stars, and 1 star, right? So in the equation of x1 plus x2 plus x3 equals 6, this is represented by x1 equals 2, x2 equals 3, and x3 equals 1. Similarly, if we have this configuration, can anyone tell me what this is in the chat? What is x1, what is x2, and what is x3? Just type it into chat. Yeah, x1 equals 1, x2 equals 0, x3 equals 5. It's pretty straightforward. So now if we count the total number of symbols, which is stars plus bars, and we need to divide n items into k groups, we have n stars and k minus 1 dividers or bars. So the total number of symbols that we use is n plus k minus 1. Right? Because in this example, with 6 stars and 2 bars, or 6 stars and 3 groups, because the number of bars is always the number of groups minus 1, we have 1, 2, 3, 4, 5, 6, 7, 8 elements or items or symbols. And essentially, we don't really care where we put the bars right now because they could also contain nothing. So we just want to take k minus 1 bar positions from a total of n plus k minus 1 possible positions. Right? It's basically just the combinations, but with bars and with total symbols. We don't really care about stars. Or we can just view this as putting n stars into a possible configuration with n plus k minus 1 total stuff. Right? Because this is an item, this is an item, this is an item, this is an item, this is an item. Right? So we have 8 items. And then if we choose where we put the bars, we have 2 bars. So the answer would be 8, choose 2. And over here, we used an example where the number of stars is greater than the number of bars, right? But can the number of bars be greater than the number of stars? Can anyone tell me in the chat? Just say yes or no. Remember that in each group, we haven't said that they have to have at least one item in it. It can also have 0. In this example, we have 0 in one of the groups. So can the number of bars be greater than the number of stars? Yes, it can. So we can also use this example of 2 stars and and a bunch of bars. This also works because we haven't put any restrictions yet. And in this case, how many ways can we arrange the bars? Can someone tell me? If we have 7 bars and 2 stars? You don't need to calculate the exact number. Just tell me in terms of something, choose something. Remember, n is the number of stars, k is the number of bars. Here, n is 2 and k is 7. So we have 2 plus 7 minus 1. Oh, choose 7 minus 1, which is equal to 8, choose 6. Which is also equal to 8, choose 2, which is equal to 28, I think. So in this example problem, Pat wants to buy 4 donuts from a supply of 3 types of donuts, glazed, chocolate, and powdered. How many selections are possible? So over here, we have 4 donuts, right? Which is 4 stars, because we haven't classified them into types yet. And then we have 3 types, which is, oh, whoops. If we have 3 types, then we have 2 bars. Wait, no. It's right. If we have 3 types, then we have 2 bars. So we look at the number of types, which is 3. Right. So it will be 4 plus the number of bars, which is 2. So it's 6, choose 2. Because we just want to put the bars into places, into positions, I mean. Over here it should be, whoops, I think I made a mistake. Should be 2 plus 7 over 7. 2 plus 7, choose 7. Yeah. So it should have been this. And in this case, we have 6, choose 2. And 6, choose 2 is just 15. Yeah. Does anyone have any questions? I think I might have accidentally confused some of you by doing the wrong formula for the one above. It's the number of stars plus the number of bars. Choose the number of bars. How do you insert that into a calculator? I actually don't know because I usually just do this in my head. But if you have a complex or like a big number, then you probably need your calculator. You can find a YouTube video on that, I think. And it depends on the type of calculator you have. So a common scenario is that we have the restriction of each group having at least one object or one item. So in this case, we have that all of the x of x1, x2 through xk must be positive, right? Because they all have at least one object. That makes sense, right? But then how's this different from the case that we just had? How's this different from this equation?
You can't have none.
Yeah. So the main difference is that you can't have groups of 0 anymore. Where is it? So how should we fix this issue? Can someone tell me? Does anyone have any ideas how we can fix this? By going back to the original case? Here's a big hint. It says at least 1, right? But then in the other one, we had at least 0. How can we get from 1 to 0? Can someone tell me in chat? Okay, so to get from at least 1 to at least 0, we can just subtract 1 from all of the x1, x2, all the way to xk. Oh. So we can just turn x1 into x1 minus 1, x2 into x2 minus 1, all the way to xk equals xk minus 1. So we have x1 dash equals x1 minus 1, x2 dash equals x2 minus 1, and xk dash equals xk minus 1. But then if we take away 1 k times from the left-hand side, what do we have to do to the right-hand side in order for both sides to stay equal? We have to take away k from the right-hand side as well, right? Which is why we have x1 dash plus x2 dash plus all the way to xk dash equals n minus k. And then if we plug this into our formula over here of n plus 1, n plus k minus 1, choose k minus 1. What do we get? We get n minus k plus k minus 1, choose k minus 1. And to make this a bit clearer, we get exactly n minus k plus k minus 1, choose k minus 1. And this cancels, so we get that this is n minus 1, choose k minus 1. If we're separating n items into k different groups, and all of the groups must have at least one item. So expanding on this case, if we have at least r in all groups, then we can subtract r k times from the left-hand side to get x1 dash all the way to xk dash equals n minus k times r, right? And then we can just alter our formula into n minus kr plus k minus 1, choose k minus 1. You don't need to memorize this formula. As long as you understand the process, then it's pretty straightforward. Does anyone have any questions? I'll take the silence as everyone is understanding. So here are some practice questions. How many 4-digit numbers have digits that sum to 10? I'll give you guys 3 minutes to try it out. So I think the first step that you should try is try to turn this into an equation. And then if it has any restrictions, then you can alter the equation a bit, and then you can just plug it into the formula that we had at the start. I'll just write the formula out for you guys. Wait, I think I have the question. Yeah. So this is the question. And the formula is wait, does everyone know what an integer is? It's just a whole number, right? So non-negative integers are whole numbers from 0 to infinity. Give you guys 2 more minutes to try this question. If you have any questions or if I explained anything unclearly in the prior slides, just type it into chat. Okay, so firstly, how should we view this question visually? Can anyone tell me how we can view this visually with stars and bars? Okay, how many stars do we have? Just type it into chat. 10 stars, right? Oh my God. Wait. I think this should be 10 stars. Yeah. So we have 10 stars, and how many groups do we have? Type it into chat. We have 4 groups, right? So how many dividers or bars do we have? 3, which is 4 minus 1. So basically, all of our solutions will look like something like this. Oh, right. And in this case, this example, we have the number 4, 2, 2, 2. We have 4 plus 2 plus 2 plus 2 equals 10. Right? And is there any restriction in the question? Can someone tell me in the chat? Are there any restrictions like some number has to be positive, some number has to be greater than some number? One of the xi has to be, yeah. So the restriction is that x1 cannot be 0, right? It has to be at least 1, in other words. So how can we fix this? How can we revert this restriction back to the original conditions of non-negative? Because now it has to be positive for x1, and that's not very good for us. Can someone tell me in the chat? Here's a hint. Before, we just took away 1 from all of the necessarily positive numbers to get x1 dash through xk dash. So how can we deal with our current problem of x1 being positive? It's actually more simple than before. Before we applied this transformation to all x1, x2, all the way to xk, right? But now we can just apply it to x1 by itself. So we simply just do x1 dash equals x1 minus 1. And that's it, right? So we have x1 dash plus x2 plus x3 plus x4 equals 10. Am I missing something? If I'm missing something, can someone tell me in the chat? What am I missing from this equation? Because before we had x1 plus x2 plus x3 plus x4 equals 10. But now I transformed x1 to x1 dash by taking 1 off x1, and we have 10 on the other side. What's wrong with this new equation that I just made? This is a common mistake made when doing stars and bars. What mistake have I made? Yeah, I did not change anything on the other side. What do I need to change on the other side? Yeah, you have to minus 1, right? So when you're new to a complex idea, I guess, in math, it's best to write out every step because if you skip any steps, you'll probably make a mistake like this one. So over here, we did x1 minus 1 plus x2 plus x3 plus x4 equals 10 minus 1, right? And then we just turn this one into x1 dash. And now, can anyone tell me how many solutions this has using the prior equation? You don't need to tell me the exact number. Just tell me some number, choose another number. Like x choose y or something. Or a choose b. It's not that hard. We just apply the same exact formula of this to this new equation. Okay, how many x's do we have? We have 1, 2, 3, 4, right? We have 4 items, or 4 groups, I mean. So we have k equals 4. And what is n? N is the number on the right-hand side, right? Over here, it's 10 minus 1, which is 9. So n equals 9.
So
And now we can directly... Oh, what did you ask?
was it 4 choose 9?
Should be the larger number choose the smaller number, right?
9 choose 4.
Not quite. So it's actually, the answer is n plus k minus 1 choose k minus 1, right? Because we have new n and new k, we can just... Oh, I mean k is the same as before, but we can do k dash. So this is just equal to... Oh, I think 12 choose 3. Right, because we do 9 plus 4 minus 1, which is 12. Choose 4 minus 1, which is 3. And this is equal to 12 times 11 times 10. Oh, whoops, why did I write that? Divided by 3 times 2 times 1. Right? Because we just divided by, we just canceled out the 9 factorial. Because originally it's equal to 12 factorial over 3 factorial times 9 factorial. Right? Yep. And this is just equal to 11 times 10 times 2, which is equal to 220. And we are done. Okay, the next question is pretty straightforward. How many integer solutions to x1 plus x2 plus x3 plus x4 equals 25? If x1 is strictly larger than 0, x2 is strictly larger than 1, x3 is strictly larger than 2, and x4 is strictly larger than 3. I'll give you guys 4 minutes to try this question. Well, actually, I'll give you guys 2 minutes to try this question. You don't need to find out the exact answer, just tell me in terms of one number, choose another number. Okay, so basically in this question, I did the strictly greater than signs to throw you guys off because before we had non-negative, which means they could be greater than or equal to 0 and greater than or equal to 1, right? But over here, I used strictly greater than, which means x1 is greater than or equal to 1, x2 is greater than or equal to 2, x3 is greater than or equal to 3, and x4 is greater than or equal to 4. And if we write this out, we have, oh wait, no. We can use the same strategy as before by just subtracting the minimum value from all of these to get that they are non-negative, right? To revert back to this equation. And now we can do x1 minus 1 plus x2 minus 2 plus x3 minus 3 plus x4 minus 4 is equal to 25. And then what did we do? We took away 1, we took away 2, 3, 4, which means we took away a total of 10. And then from this, we get x1 dash plus x2 dash plus x3 dash plus x4 dash equals 15. Plugging this into the original formula, we get the number of solutions is equal to 18 choose 3, I think. Yeah. Is this straightforward? Okay. We'll go through some binomials now. This is a bit of algebra. So can we all expand a plus b squared, a plus b cubed, a plus b to the 4, a plus b to the 5? And do you notice a pattern in the coefficients? It's fine if you don't, because the pattern is pretty hard to spot. Just do a plus b squared and a plus b cubed for now. And then I'll go over the others. I'll give you guys half a minute. Yeah, Chris, that's right for a plus b squared. What about a plus b cubed? Yeah, Kingsley, that's the main idea of the whole thing. So this is a plus b squared. A squared plus 2ab plus b squared. A plus b cubed is a squared, a cubed plus 3a squared b squared, a squared b plus 3ab squared plus b cubed. And then if we continue, we get a plus b to the 4 equals a to the 4 plus 3a, plus 4, a 3b plus 6, a squared b squared plus 4ab cubed plus b4 and a to the 5, a plus b to the 5 is equal to a to the 5 plus 5, a 4b plus 10, a 3b2 plus 10, a 2b3 plus 5ab4 plus b to the 5. So if we look at the coefficients, which is the number before a to the power of something, b to the power of something, we get that for, we can also add in a plus b to the power of 0 and a plus b to the power of 1 if we want to make this look more clear. A plus b to the power of 0 equals 1. So does anyone see any pattern? It's pretty unclear. But if I were to rearrange these coefficients in this formation, in a triangle formation of 1, 1, 1, because we have 1 in the first one, we have 1a, 1b. We have 1a squared, 2ab, and 1b squared. So we have 1, 2, 1. We have 1a cubed, 3a squared b, 3ab squared, 1b cubed. We have 1, 3, 3, 1. And if we continue, we get 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. Can anyone tell me in the chat what this is? What this strange triangle is?
Pascal's triangle.
Yeah, it's Pascal's triangle. So what's the pattern in Pascal's triangle? Every number, except for the ones on the side, they just continue diagonally, like in one direction. You can obtain every next number below from two numbers above. So over here we have 1 plus 1 equals 2, 1 plus 2 equals 3, 3 plus 3 equals 6, like that. So this is the pattern. So this is the binomial theorem. It looks pretty intimidating. It basically states that x plus y to the n is the sum of n choose k times x to the n minus k y to the k. So we can view a plus b to the n as a plus b times itself n times, right? And this is basically just doing n groups of 1a and 1b. And then if we want to find the number of times that when we multiply this huge expression together, the number of times that we obtain a to the n minus k and b to the k, or a to the k and b to the n minus k, then we have to choose a k times from these n groups, right? So in each group, we can either choose k, we can either choose a, or we can choose b, right? Because we can't have a and b multiplying each other if they're in the same group of a plus b, right? Do you know how multiplication in algebra works? So if we have a plus b times a plus b, it can only be between groups. So we can have this one multiplied by this one multiplied by this one multiplied by this one, and this one. But we cannot have a multiplied by b in the same group, right? That just doesn't work. So going back to the topic, this means that in each of the a plus b's, we select an a or we select a b, right? And then we repeat this process n times. But then at the end, to get a to the k, to get a to the k and b to the n minus k for some number such as 1 or something, or 2 or 3, then we have to choose, we must choose a k times, right? And then the other times we can just say they all go to b. Which is why the number of times that we get this, or the coefficient in front of this, is the same thing as choosing k items from n distinct items, which is n choose k. Does that make sense, or is that a bit confusing? Can you tell me in chat? Just say yes if it makes sense. Or no if it doesn't. Okay, someone said yes, so I'll just take it as everyone. So here's some quick problems using this big formula for this. What is the coefficient of x to the 0 in x plus 1 over x to the 8? I'll just go over this one with you guys. So, wait. Oh, yeah. So in order to get x to the 0, what must we do? We must have x to the 1 chosen 4 times, and x and 1 over x chosen 4 times as well, right? Because x times x to the 4 times 1 over x to the 4 is equal to x to the 0. That's the only way we can get this power of x to the 0. That makes sense, right? Okay. I'll take the silence as a yes, which means the coefficient is number of ways we can choose 4 items from 8 distinct items, right? Which is basically n choose k. What is n? Can someone tell me in the chat? Here's a hint. So what is n in this example? 8, right? Because we're taking this expression to the power of 8. And what is k? Can someone tell me in the chat what k is? K is the number of times that we chose x to the 4, right? And how many, oh, x by itself. K is the number of times we chose x. How many times do we choose x? Well, x to the 1, we chose it 4 times, right? So k equals 8. And k equals 4. This means that we have 8 choose 4. And then, yeah. Similarly, what is the coefficient of x to the 6 and 2x plus 1 over x to the 10? I'll give you guys 2 minutes to try this question. Well, actually, I'll give you guys 3 minutes. Remember that in this case, or this question, we have 2x instead of just x by itself, which means we have to multiply the choose function by some power of 2. You guys don't need to tell me the exact number, just tell me it's like 2 to the power of this times this choose that. Okay, so firstly, how do we get the power of x to the 6 from 2x and 1 over x while choosing a total of 10? Can someone tell me in the chat? How many x's do we choose? How many 1 over x's do we choose? Because when we multiply them together, 1 over x is x to the power of -1, and 2x has x to the power of 1. Okay, I'll just tell you guys. So to get x to the 6, we need x to be chosen 8 times. Wait, that's not good. X chosen 8 times. So in this case, we have 2x chosen 8 times, and we have 1 over x chosen 2 times. Because in the expression of a plus b n times, we have to choose at least one thing from every single bracket of a plus b, right? Which means we have to choose the number of times we choose 2x plus the number of times we choose 1 over x has to add up to 10, which is why we have 8 and 2. So now this is pretty straightforward. We can just do 10, choose 2. And is that our coefficient of x to the 6, or is there another step that I've missed? This is the amount of times that we get something times x to the power of 6 within the uh, multiplication of a plus b by itself n times. What am I missing? Here's a hint. So in the expanded equation, we would have 10 choose 2 times 2x to the 8 times 1 over x to the 2, right? But then if we have 2x to the 8, we have 2 to the 8, well, times x to the 8, right? So the number in front of x to the 6 must be 2 to the 8 times this choose function, right? Does that make sense? So the number in front of x to the 6, or the coefficient of x to the 6, will have to be 2 to the 8 times 10 choose 2, which is 45, or 256 times 45. Okay, we'll finish off the rest of the slides next time. But if you just look through the slides in your spare time, then it'll be pretty straightforward. Except for the hockey stick identity, this is pretty complex. You don't need to learn it if you don't want to, because it leads into pretty advanced stuff. Just try most of the handout questions, and I've attached most of the sources to the handout questions, such as AIME 1988. And sometimes, wait, yeah. So this is 2012 AIME 2 instead of AIME 1. So if you want the exact source. And yeah, it should be pretty straightforward. But some of these questions are very hard. How did everyone find the questions today? Were they hard? Were they easy? Or were they just right? Can you tell me in the chat? Because I think I might have made them a bit too hard. Oh, okay, a little hard. Yeah. Oh, okay, sorry. Has anyone tried out the handout questions? because they are like at least a step above the slideshow questions. But most of them you can find the answers to online, so it should be understandable at least. Maybe not problem 1. This one is pretty difficult. Problem 3 is derangements, which is basically just rearranging, except you can't have any repeats. And it's from, I think, AIME. This question is pretty fun. I can explain it next time. And then this one is pretty elegant as well. I'll explain this next time. This one is very hard, so it's just attempt it if you fully understand today's material. Problem 7 in the handout is pretty straightforward. You can probably do this right now. Problem 8 is very straightforward. You just plug it into the equation. Problem 9 is slightly difficult, but you should be able to manage. You just expand both sides. Problem 10 uses problem 9. And if you don't understand sigma notation, that's fine. I'll cover the handout questions next lesson. Problem 11 is just straight application of the formula. Problem 12 is very common in math competitions, especially AMC. So if you're doing AMC, you should learn to do problem 12. You can also just search up the problem online if you want the answer. And then problem 13 is pretty difficult to understand, but it should be easy to prove. Okay, thank you for coming. See you.